So today, we're going to look at something really cool, a programming language called CLACL, and it completely throws out the rulebook for how you create shapes. It's all about generative geometry. Sure, but with a twist that makes you think less like a drafter and, well, more like a philosopher.
All right, let me start with a little puzzle for you. How would you, tell a computer to create a perfect square, but with one major catch? You can't use any coordinates. No x, no y, no draw line from here to there. I mean, it sounds kind of impossible, right? Well, that is exactly the kind of problem CLACL was built to solve.
So this is all about geometry without coordinates. It's about a fundamental shift in how you think, from points to rules. The whole idea with CLACL is that you stop thinking about plotting points on a grid. Instead, you're just defining the rules of a shape. You're not the artist, you're the lawmaker.
Let's break this down. On the left, you've got the traditional way, imperative drawing. You're basically micromanaging the computer, right? You're telling it how to do everything step by step. Go here, draw this. But on the right, that's the CLACL way. It's declarative. You don't tell the computer how, you just tell it what is true. You simply say, hey, a side relationship exists between A and B, and then you let the system figure out the rest. And this quote, this really gets to the heart of it. The space we're generating isn't a picture. It's not graphic at all. It's logical. It's relational. See, CLACL isn't working on some digital canvas. It operates in what's called the space, a purely conceptual realm where things are defined by how they relate to each other, not where they sit on a grid.
Okay, so how do we actually write these rules? Well, the beauty of it is that the entire language is built on just three simple fundamental building blocks. Let's take a look. First up, we have the instance, and you write it with an exclamation mark. Think of this as the absolute atom of our logical universe. When you type 1A, all you're doing is stating that a concept named A now exists. That's it. It has no position, no size, it just is. It's the most basic thing you can possibly say. Next up, the relation, which you mark with an ampersand. Now, if instances are the atoms, relations are the bonds that connect them. It's just a rule that links instances together. So for example, if we write and diagonal, then blat A, blat B, we're not drawing a line. We're simply declaring that a specific logical relationship called diagonal now exists between the concept A and the concept B. And finally, we have the model. And this is where CLACL gets really powerful. A model is basically an abstract blueprint. It's a way to package up a bunch of instances and relations into a reusable idea, like the very concept of squareness itself.
All right, so we have our three building blocks. Let's go back and solve that mystery from the beginning. We're going to build a perfect square, starting from absolutely nothing, using only these logical rules.
Okay, step 1. We create our foundation. We just assert two instances into our empty logical space, at A and at B. That's it. You can think of these as the two opposite corners of the square we're about to make. Now for step 2, where we define the core relationship. We simply state that a diagonal relation exists between A and B. And with just that one line, we've given the system all the geometric information it needs. It now understands the distance and orientation that are implied by this single logical link. And here comes the magic. We now add rules for the sides. We say a side relation exists between at A and some new instance, let's call it at C. And we also say a side relation exists between at B and that same at C. Based on what it knows about diagonals and sides, the system has only one logical choice. It generates at C in the exact position that makes both rules true. We do the same thing for at D, and just like that, our square is complete. And here it is, the final script. Just a handful of declarations. We didn't draw a thing, we just described a set of truths, and the system generated the only possible shape that could satisfy them. No coordinates, just pure logic.
Now that's already powerful stuff, but it gets so much better when we start using models. This is where you see the real potential of defining systems with abstract rules. So instead of writing out all those rules every single time, we can wrap them up in a model called Square. This model is our blueprint. It's a recipe that basically says, to be a square, you need a diagonal between 2 points and 4 side relations that connect to 2 other points that get generated. And it is crucial to understand the difference here. Define model, that's the blueprint, the architect's drawing. It's just an abstract idea. But applying the model square, at A, at B, that's like actually constructing the building. We take the abstract concept and apply it to our real instances to generate a real shape, and you can use that one blueprint to build thousands of different squares. So here is the big question. What do you think happens if we go back into our abstract blueprint and change just one single tiny rule? Let's say we edit our square model and change the relation and side to a different, predefined relation we'll call and curve. A single word is changed in the abstract definition. That's it.
And this is the payoff. By changing that one line in the blueprint, every single square we created using that model, whether it's hundreds or thousands of them, instantly transforms. They all become these new shapes with curved sides. Because we didn't change the instances themselves, we changed the fundamental rule that governs what it even means to be one of those things.
So let's wrap with the key takeaways. First, CLACL is about describing rules, not drawing points. Its simple building blocks, instance and relation, can create incredibly complex logic. Models let you build powerful and flexible blueprints, and most importantly, changing one central rule can transform an entire system in an instant. This leaves us with a final thought. I mean, if we can describe the logic of a square into existence without ever drawing it, what else can we define this way? Music? Organizational structures? Maybe even biological systems? If code can describe geometry, what other complex systems can we literally describe into existence?